Hi, this is Dave Johnson with another edition of Math Off Topics. Today I'd like to derive, and I'm going to put that in air quotes, the definition of the derivative. Now we all know that the derivative is defined in a certain way. And so trying to derive a definition is kind of silly. But if by doing this kind of exercise, we actually understand the process better, we understand what the requirements are, say, for the derivative and other things. So now what's going to be driving this derivation? Well, what I want to do is I want to use a function that has a Taylor series. And of course, that means it has derivatives, okay? But that doesn't necessarily say how those derivatives are calculated. And secondly, I want to use the, the fact that with a derivative, you get a good linear approximation to the function. And that's a key idea. In fact, in calculus 3 or 4, you might even see a definition or a theorem that says that a function is differentiable if it has a good linear approximation. Okay, so let's get into it. So here's our Taylor series. And so f of x evaluated, so the expansion is about x naught, just some arbitrary x. And let's call these higher degree terms e of x, which means the error between the original function and its linear approximation. So here's the linear approximation here. What is e of x? So e of x is equal to f of x minus this quantity f of x naught plus f prime of x naught times x minus x naught. And we want that the limit as x approaches x naught of e of x divided by x minus x naught to be 0. Now let me say a couple of words about this. So first of all, we want this error to go to 0 very quickly, right? If we've got a good linear approximation, then for small x minus x naught, we want these terms to go to 0 very quickly. Now, how do we realize that? Well, if you take the limit of this ratio, in order for a limit of a ratio to be 0, the numerator has to go to 0 a lot faster than the denominator. Otherwise, it just won't happen that this will go to 0 in general. So in order, and that would give us a good linear approximation. So let's assume that for small x minus x naught, e of x is going to be 0. Now, how do we make that happen? Well, if I say f of x minus f of x naught plus f prime of x naught times x minus x naught, if that's equal to 0 for small enough x minus x naught, okay? So now we're going to solve this equation, and we get f prime of x naught times x minus x naught is equal to what? Well, it's f of x minus f of x naught if we distribute and solve. And then the next step is let's divide through by x minus x naught. And again, this is only going to be true for small x minus x naught. So f prime of x naught is now equal to f of x minus f of x naught divided by x minus x naught. But this, again, is true only for small, very small, sufficiently small x minus x naught. And so I can rewrite this as f prime evaluated at x naught is equal to the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. And that's exactly one of the classic definitions for the derivative of the function f. So again, we haven't derived the derivative. We've shown the connection between the derivative and linear approximations for functions of one variable. I hope you've enjoyed this video. If so, please like and subscribe, and I will see you in the next video.